All right, in this video, I'm going to overview the background sections of Lab 8. There are two of them. The first is on Hubble's law, and the second is on cosmological redshift. Let's take a look at the first. Hubble's law is a plot of two things for galaxies. On the x-axis, we plot the distance to the galaxy, how far away it is. On the y-axis, we plot the galaxy's apparent recessional velocity, or how fast it appears to be moving away from us. And I say apparent and appears for a specific reason, which we'll get to in the next background section. So distance on the x-axis versus velocity on the y-axis. Now, we learned how to measure distances and velocities in previous labs. In Lab 5, we learned how to measure the distance to nearby galaxies using Cepheid variable stars. And we learned how to measure the distances to faraway galaxies using type 1a supernovae. So that's how we measure the values for the x-axis. For the y-axis, how fast the galaxies appear to be moving away, we can use the Doppler effect, which we learned about in Lab 7. And that's given by this equation, where the velocity of the object is equal to the speed of light times the redshift, and the redshift of the object is equal to the change in wavelength divided by the emitted wavelength, where the wavelengths are measured from the spectrum of the object. So, Hubble measured these quantities for a whole bunch of galaxies and plotted them. And quite to his surprise, he found this linear relationship. So, a couple things about this. First of all, it means that all the galaxies in the universe, except for those that are very, very close to us, are moving away from us. It's like nobody in the universe likes us. Everyone's trying to get away. Now, the galaxies that are very, very close to us, like our sister galaxy, Andromeda, or the other galaxies in our local group of galaxies, they are gravitationally bound to us and to each other. And so they can be moving towards us due to our mutual gravitational attraction. But once you get out beyond the local group, everything's moving away from us. Second thing about this plot is the linear relationship. It means that nearby galaxies are moving away at a certain speed. Farther away galaxies are moving away even faster, and even farther away galaxies are moving away even faster beyond that. It's a rather unusual and peculiar flow of material. Now, you see some scatter in this plot, and that's because these galaxies caught up in this cosmic flow are also being tugged on by other nearby galaxies, like we are tugging on Andromeda, and Andromeda is tugging on us. This will cause some of the galaxies to flow away just a little bit faster, or not quite as fast, depending upon the direction of these nearby gravitational tugs. So that accounts for the scatter, but the scatter aside, this is a pretty linear relationship. So let's think about what that means. If nearby galaxies are moving away at a certain speed, and farther away galaxies are moving away even faster, if we reverse the clock and run time backwards, that means those faraway galaxies would be moving towards us pretty quickly. The nearby galaxies would be moving towards us, but not as quickly. And if it is a linear relationship, that means if you keep running time backwards, you'll come to a time when everything is on top of everything else. We call that the Big Bang. And for this flow, that would be 13.8 billion years ago. Now, if you run time forwards again, everything will be flowing away from everything else, flowing away from us, and that feels like an explosion. But as we talked about in a previous overview video, that is a misconception. So let's explore why that's a misconception next. One of the reasons why this can't be an explosion is because if it was an explosion from a single point in space, what we would expect now is some shell of material moving outwards. So all the matter and energy in the universe would be distributed in some shell. However, when we look out into the universe, we don't see this. All the galaxies appear to be distributed homogeneously, which means the same numbers in all locations, and isotropically, meaning the same numbers in all directions, at least on very large scales. On smaller scales, the material clumps because of mutual gravitational attraction. To see this, take a look at these two slices of a large galaxy survey. This is a survey of the galaxies in the observable universe. And in this plot, each point corresponds to an entire galaxy. We are located at the center of this plot. So you may notice the farther out you go, the fewer galaxies you see. However, this is not because there are fewer galaxies out there at great distances. This is simply because the farther away the object is, the fainter it is, the harder it is to detect, and so we see fewer and fewer of them. However, we understand the sensitivity of our instruments, and when you correct for that sensitivity, what you get is that the galaxies are distributed uniformly throughout all of space. Again, on large scales. On small scales, you can see the material clumps gravitationally. However, what we don't see in this plot is a single large shell around some point in space, which is what you would expect if the Big Bang was an explosion of material from a single point in space. Let's consider another reason why this can't be an explosion in space. What we're looking at here is the Hubble Deep Field. It's a very small piece of the sky that the Hubble Space Telescope stared at for a very long time and found thousands upon thousands of galaxies. Now, in this particular figure, a handful of them have been labeled with their redshifts, measured from spectra taken of these galaxies. And I've circled the ones with redshifts greater than 1. Now, if we interpret these as motions through space, then the Doppler shift equation applies. And here it is again, where the velocity of the object is equal to the speed of light times the redshift. And a redshift greater than 1 would then imply a speed of the object greater than the speed of light. And we all know, Einstein showed us, that nothing can travel through space faster than the speed of light. Now, technically, this equation is an approximation, and it breaks down when objects travel close to the speed of light. If you use the full-blown version of the equation, A redshift greater than 1 doesn't actually mean that you're traveling faster than the speed of light. It means that you're traveling very close to the speed of light. However, objects that travel close to the speed of light exhibit all sorts of peculiar behavior. This comes from Einstein's special theory of relativity, which has been confirmed on high-speed particles and other experiments here on Earth. Basically, if something is traveling through space close to the speed of light, for that object, time will slow down. It will appear to be moving through time more slowly. Its length will contract in its direction of motion, and its mass will increase without bound as you approach the speed of light. And when we look at these high redshift galaxies, we don't see any of that behavior. So, whether you're using the approximation or the full-blown equation, these redshifts greater than 1 are just not consistent with motion through space. So, how can Hubble's law be explained, if not due to the motion of galaxies through space? Well, Einstein showed that space itself can move. So we don't have to try to explain the expansion of the universe by galaxies moving through space, but rather by space itself expanding, with everything in it being carried along for the ride. We can see that in this figure here, where you have a two-dimensional representation of space full of objects. And as that space expands, the objects move apart from each other, not because they're moving through space, but because space is expanding, taking them along with it. Now, in reality, space is not two-dimensional, it's three-dimensional. So here's another way to envision this. This is the raisin bread analogy. Imagine a loaf of raisin bread, and here they've drawn the raisins in on some nice uniform grid, a very organized loaf of raisin bread, makes it easier to see what's going on. And in this analogy, the raisins are like galaxies and the bread is like space. And so you put this loaf of raisin bread in the oven and start baking it, and the bread expands, carrying the raisins apart from one another. Now, a loaf of raisin bread has boundaries. It has a top and bottom and sides. And space has no boundaries. It goes on and on forever, at least as far as we can tell. So one way to think about the universe is like an infinitely large loaf of raisin bread, expanding, carrying everything in it apart from everything else. Now, some people, myself included, have a hard time thinking about physical infinities, about space going on forever and ever and ever. That's possible in Einstein's equations. But there's another possibility in Einstein's equations, and that's that space wraps around back onto itself, kind of like the surface of the Earth. If you go along the surface of the Earth in a constant direction, you end up where you started. And the same would be true for space in this case. We can't visualize it because it requires thinking of three-dimensional space curved in some fourth dimensional embedding space. We can't visualize that, but we can think about it one dimension down. For example, here we have coins taped onto the surface of a balloon. In this example, the surface is space. The inside of the balloon, the outside of the balloon, that's nothing. The surface is space, and the coins are galaxies. So as you blow up the balloon, the coins, the galaxies, move apart from each other. So whether space is infinite in extent or if it wraps around upon itself and is finite, you can explain the expansion of the universe as an expansion of space instead of an explosion of material from within space. Now, what about those redshifts greater than 1? Well, objects can't move through space faster than the speed of light. Space itself can expand at whatever speed it damn well pleases, carrying the objects within it apart at what appear to be faster than light speeds. Again, the objects are not moving through space faster than the speed of light, so we're not breaking any rules. They're being carried apart by space itself at greater than light speeds. Anyway, I like to think of the Big Bang not as an explosion in space, but an explosion of space. Okay, let's take a look at our last background section on cosmological redshift. So if this is not motion through space, there can't be a Doppler effect. The Doppler effect is produced by objects moving through space. So if these are not Doppler redshifts, what are we measuring? And the answer has to do with light and the fact that light has no internal cohesion. As the universe expands, so does any light that happens to be traveling through it. And as light is stretched out to longer and longer wavelengths, it becomes redder and redder in color. Now, you may ask, do you expand with the universe? And the answer is no. You're made of molecules. These molecules have strong intermolecular bonds that hold you together against the expansion of the universe. What about the Earth? Does it expand with the universe? And the answer is again no. Earth is held together by gravitational forces, and these forces are strong enough to hold it together against the natural expansion of the universe. The same is true for our solar system, our galaxy, and our local group of galaxies, including Andromeda. But once you go further out than that, the objects are farther apart, the gravitational forces between them are weaker, and the expansion of the universe wins out, carrying everything apart from everything else. Since light has no internal cohesion, as the universe expands, it gets stretched out. And the longer the light travels through the universe, the more stretched it gets. So the more distant the object, the longer the light has to travel, the more redshifted it is by the time it gets to us. And that is, after all, Hubble's law. The greater the distance, the greater the redshift that we measure. Now, sometimes, like we saw in this figure before, we take these redshifts and multiply by the speed of light to turn them into Doppler velocities. But these are only apparent velocities. Again, these objects are not moving through space. This is not a Doppler effect. It's caused by the stretching of space itself. Now, to distinguish these redshifts from Doppler redshifts, they have a different name, and we call them cosmological redshifts. Okay, so just to wrap it up, here's a figure that we saw first in Lab 4, and this is the cosmic distance ladder. Much of this course has been organized around the cosmic distance ladder, and now we have a new final and ultimate rung to this ladder, Hubble's law. We can use Hubble's law. Once it's measured and determined, we can use it to measure distances all the way out, farther than any of these other methods can take us. all you have to do, you have some distant galaxy, you take a spectrum of that galaxy, measure its redshift, and then you can use Hubble's law to figure out its distance. For example, if you measure a redshift of 0.08, which is right here on this figure, that corresponds to a distance of a little bit more than 300 megaparsecs. Okay, that's it for this overview video.